this is the first math session in our class. That means this is week 1. And what we have, we will start with chapter 6 as per syllabus and follow chapter 7 and then chapter 11 and 10. It's a little bit different order than the textbook, but that's how the syllabus is like created. Okay, that means chapter 6, week 1 will only cover section 6.1, which I will talk today, and then the section 6.2, 3 and 4 are talking about the logarithmic and exponential function. And if you've checked the textbook, because I don't know if you have the hard copy, but doesn't matter, I can show you something. Probably we can't really see. Some of the pages are blue. Okay, that's what we have in the textbook. Section 6.2, 3 and 4 are covered twice. That we do have a normal white pages, and again after section 6.4, the white pages, we do have another set of these 3 sections with the blue pages, and it's just a little bit different order to introduce the topic, the concept. Okay? That means what we will do, I will follow the order with the stars, 6.2, 3 and 4, which is the blue pages. But again, doesn't really matter. You can rely on my session and you can rely on my slides, and I will try to take all of the important information to the presentation, and you can study from this. Okay, because always is a little bit like of confusion. I always get few emails like how we can study, but if you're not gonna read the textbook for this section, you can just follow this, because I will try to introduce in the nice order. That means what I will do, again 6.1, and for the section 6.2, 3 and 4, we do have three main parts. We have to talk about the limits of the logarithmic and exponential function. We have to talk about the derivatives and integrals. That means today I will try to talk about the limits and derivatives only, and integrals we will leave for the next week. Okay, that means let's start. I will switch off my video because it's just a better connection, and let's start. Yeah. Any question, you can use the chat box. Any question I ask, you can use the chat box to answer. That means what we have. 6.1, inverse function. Oh, I can't change my slide. That's what we will do. We will talk overall, general, about the inverse functions. That means one of the important and essential property that functions should have, in order to have its inverse, function must be 1-to-1. Okay? That means this is a little bit of algebra review. Hopefully you remember, but I can show you the definition. That means function is 1-to-1, okay, if it never takes the same value twice. Okay? That's the shortest definition, which means for every different axis, we will always have 2 different outputs. Because we know we do have a quadratic function, for example, the basic quadratic function x squared, that's y, that's x, that's the formula, x squared. And for 2 different x's, like -2 and 2, I do have the same output, 4. Because squaring positive or negative doesn't really matter, we will still get the positive. And if the absolute value of these numbers are the same, the output is the same. That we can see function x squared on the entire interval from -infinity to +infinity is not 1-to-1. Okay? That's not a 1-to-1. And what we can do, we can use the horizontal line test as a tool to test the function. That means you can see I kind of have a quadratic function, but the upside down, the negative leading coefficient, and drawing a horizontal line and having 2 points of intersection will indicate that the function is not 1-to-1, because I do have 2 values. It's still a function, because for one x, it's exactly 1 y, but the same y is used for other x. That means that's not 1-to-1 function. Okay? That means function must be one-to-one in order to have inverse. That means please remember, that's not a one-to-one. And we can check. Okay? Of course, that's the tool. Okay. That means now what I have? I do have a definition of the inverse function. Okay, let's see. Let f to be one-to-one function, of course. That means we assume that we did check that the function is one-to-one with the domain x and the range y. Then the inverse function, and the notation is, I don't want to say f to the -1, but it is like -1 is placed in the power place, the exponent place. But it's not really the reciprocal, it's just the notation for the inverse. Okay? That means f, and we actually call f inverse. Then the f inverse has a domain y and the range x. So you can probably see right away what's happened. We interchange x and y's, domains and range. And that's the notation. I can, because since I have the implication both ways, I can start reading from the right-hand side. If f of x is y, then f inverse of y is x. For any y in the domain y, because it's going to be the domain. And that we can see f inverse of y is x, then we can switch. I mean, this is the first thing that we have to remember for section 6.1. We do have two definitions, okay? But we can see it's relatively simple, but it's so important. Always the simplest stuff are the crucial. Okay, so now I do have a few information. Domain and range is interchange, of course, and this is just, I want to make sure that you understand that this notation means inverse, doesn't mean this. F inverse of x is not the reciprocal. If we would like to have a reciprocal, I have to hug everything to the -1. Then, yes, then I can flip a function. This is an inverse, that's the proper power, but not this. Okay? And then we have a first question. Which of the following function has its inverse on the interval? Which basically this question is asking if the following functions are one-to-one. Okay? We're not going to look at the inverse at the moment, but we're just testing if it's one-to-one on the entire domain, because I believe each of the function has domain all of the real numbers. Okay, function number 1. Can you tell me, is function f of x equals to x one-to-one or not really? I will put the numbers. It is one-to-one, of course. I can draw maybe, it's simply this function, okay? And if I will draw the vertical, the horizontal line, always the horizontal line will intersect once. That means, yes, this function has its inverse, it's one-to-one. We can say 1-to-1. Okay, what about x squared? Of course, oh, thank you, wow, you fast. Okay, I can draw maybe x squared here, y and x, and of course, function x squared is not really one-to-one, because for two different x's, we do have the same value, y. Okay? But I don't know, I can make a small comment, because you probably noticed in chapter 6, we will talk about the inverse function of trigonometric functions. Okay? And this is actually big deal, I would say, the big part of calculus. And you may probably notice that trigonometric functions, like I can even take the first one, I'm not going to talk about a lot, but just sine function. Yeah? They are periodic functions. That's the sine function, right? That means they repeat every 2 pi, 0, pi, 2 pi. Every 2 pi is the same situation. That means, what do you think? It's sine function a one-to-one function? It's, yeah, thank you, Ryan, thank you. Minha, I don't know, oh, I think I make a note. Chan, and Joe. Okay, that we can see is no. Thank you for the answer. Sine of x, I mean all of the trigonometric functions are not one-to-one, and we still talk about the inverse. That means what we will do, I will skip this one for now, but I will focus on x squared. That means what we can do, we can try, that's what mathematician wants to do, because they still don't want to leave the function. They, for example, x squared, if we would like to find an inverse, we have to make that curve one-to-one. Okay? That means one of the way is to restrict the domain. Instead of taking the entire function, let's just take the part of the x squared that is defined on the interval from 0 to infinity. That we can see only that part. And what do you think? Function x squared on that interval is one-to-one? Of course, sure, thank you, it is. That means, remember, if somebody has a problem that the function is not one-to-one, theoretically, we can make any function one-to-one, restricting the domain. Like taking just the part, like a segment, like a part of the curve. Okay, that means this function is definitely one-to-one because it's just one line, one intersection with the horizontal line. Okay, okay, that's okay. I can put no because I have to follow the main question. It's not one-to-one on the entire interval. Okay, what about x cubed? X cubed, yes, of course, because we can cube. That's function x cubed, and you can probably picture this. Any horizontal line will intersect once. We don't have two numbers that the cube will be the same. That means this one is one-to-one. Okay, what about cube root of x? Which actually, yes, cube root of x is the inverse function of x cubed. We will do this exercise. And the inverse, this will be cube root of x. That's x, that's y. And the same thing. We don't have, and two different x's will not give me the same cube root. Okay, that means this one is fine. What about cube root of x squared? And this is also one of the, it's no, yeah, okay, thank you, that's the correct answer, because we squaring, that's we can get the same value, right? And cube root of x squared, it's similar function to this one, but these negative values will become positive and a little bit up because it's squared. That means we will have, the function looks like this. Okay, this is cube root of x squared. And of course, it's not one-to-one because we do have the same value taken twice. Okay, and what about absolute value of x? Of course not, because similar idea like x squared. Oh, that's 0, 0. This is absolute value of x, and it's taking the values twice. Okay, because positive and negative has the same distance to 0. Okay, that we understand this. But please remember, you can take any function and make one-to-one, like I did with this one. Yeah, just restricting domain. Another thing, like a little bit like, because we are a little bit more professional, this is calculus too. That means how we can recognize that the function is one-to-one, not always like drawing a horizontal line, because we will not always have a graph of the function. Yeah? And not always will be easy to sketch to get the graph. But you can probably notice if the function is one-to-one, like x cubed or cube root of x, or even this, just the half of the parabola, yeah? We can definitely see that function is strictly increasing, or of course strictly decreasing, because I can also have the other way. Okay? I can draw maybe negative. This will be negative x cubed, right? Which is also one-to-one. But what is my point? If the function is one-to-one, it's always just increasing, strictly increasing on the entire domain, or strictly decreasing. We can't have the situation like this one, decreasing and then increasing. That definitely will tell me that I will have on the way down, I will have value, and then on the way up, I will reach the same height. Of course, not one-to-one. That's another way to check. We can prove that the function is just increasing or just decreasing on the given domain. Yeah, that's another proof. Okay, but we will keep this for later. Okay, you okay with this exercise? Now let's just tell me this. This is probably like 1 second exercise, just practicing our formula. As I said, this is just the definition. Okay, let's see. If the inverse of 7 is, f inverse of 7 is 3, then f of 3 is, can you, of course, 7. F inverse of -2 is 1/3, then f of 1/3 is, of course, -2. F inverse of 0.1 is 4, then f of 4 is 0.1. Probably you think it's a silly question, but it's important. We have to remember to play with the values like that. Yeah? If the function and an inverse is involved, and especially if one of the value is not given. Yeah, let's say f inverse of 7 is x, I don't know. Then f of x is 7. And maybe solving this equation, yeah, will give me the value of x. Yeah, that means something like that. Yes. Yeah, thank you. It's, of course, it's yeah. Always I like to make, I hope I will try to make the entire course really, really accessible, really easy. Okay, let's see what I have. Another property, I didn't mention about x cubed and cube root of x, but we have the nice graph here. Okay, let's look at the bottom half. If we first, if we have a function and its inverse, yeah, if we can place both of them in one xy plane, which actually some of the mathematicians, they will complain about this. I don't want to go too deep, because you probably know that in order to get an inverse, which we can actually read this. Okay, let me, yeah. Let's see, because I said we have to look at the bottom half. Now let's start from the beginning. That means in order to find an inverse, yeah, we will write an equation of the given function y equals f of x, and we will interchange x and y's. Okay? We will interchange x and y's, and we will solve the new equation for y. And the new y, of course, is the inverse function, is our function. But what now my point is, if I can take equation of the original function and equation of the inverse, I can draw in one xy plane. They will be always symmetric with respect to the line y is equal to x. They will be always like a mirror image. Okay? We can see. We don't have the formulas, but if this is function, this will be inverse. If this is inverse, this is the function. Okay? That means that, and that's also quite helpful property. But what I said at the beginning, some of the mathematicians, they don't like putting function and its inverse at one xy plane. Okay? Because of course, you remember we said that domain for the function, it will be range for the inverse. That means we do have a little bit of conflict, but that's I can say like a second level of everything. It's still a property given in our textbook, okay? And we still providing this property, that function and its inverse, it's symmetric with respect to the line y is equal to x. But just in case, if you will be the math major and you will have this nice arguing situation, okay? That means you can think about this, but it's definitely true. Yeah? If we will put the graphs at one xy plane, they are symmetric. Okay. Let's see at this exercise. That means maybe we can, this is not calculus exercise, but it's still important. It's just the algebra. That means let's just try to find an inverse, and we will follow the instruction from the previous slide. I mean, this is my y, and this is my formula, x cubed. That means I do have function y equals to x cubed. In order to find an inverse, I will interchange. Y will become x, and x will become y. Simply interchanging. And now, taking this equation and solving for y. I mean, I have to take just the cube root of both sides. This will be cube root of x. Cube root of y cube is just y. I can switch the order, and my new y, it's of course an inverse. And we knew this, that for the function x cubed, the inverse is cube root of x. And domain for this function was all of the real numbers, range was all of the real numbers, and that means almost nothing to interchange. All real, all real. Okay, that means that's what I said. They are symmetric. That's x cubed, and that's cube root of x. X cubed. Yeah, we always do this. We always write, draw function. It should be a little bit more symmetric, but you know, okay, what property I'm talking about. Okay, that means that's the way, just in case if we will ask you to get an inverse. Okay? Because I can tell you, not always is easy to find a formula for the inverse function. But even without the formula, we can still do some calculus. And let's see. Actually, one more equation, also algebra, is the cancellation equations. Okay? And what we probably notice, that if I will make a composition of the function and its inverse, okay, I will always get my original input x. Because inverse, it's like, okay, let's try to answer my question. What do you think? What is the inverse algebraic operation to addition? What do you think? When I'm adding, it's of course subtraction. What is the inverse operation to algebraic operation like multiplication? Division, of course. Taking a square, like square root, what will be the inverse operation for the square, taking a square root? Just squaring, yes, okay, square, yeah. That's we can see. It's as soon as I take a value, like when I add 5 and subtract 5, I'm still getting with that x minus 5 and then plus 5, I'm getting x. That means starting with x and doing both of this, let's say addition and subtraction, I will of course cancel out in the middle and I will end up with x. That's what we call the cancellation equation, and the definition looks like this. We making a composition. We like compounding inverse operation and the original one. Original and inverse, doesn't really matter which way we will start. And we can try to look at the x cubed and cube root of x. My typing is just different, okay? That's mean what I can do. This means that I have to take the first function, which is x cubed, okay? And inside x cubed, which means instead of x, I have to put cube root of x. Okay? That means this is x cubed, but instead of x, I am putting the inverse cube root of x. But cube root of x, we know that we can write the power form x to the power of 1/3. And then 1/3 and 3 cancel out is x. Or I can do the other way. I can start with cube root of x, and inside I have to put the original function x cubed. And of course they will cancel out. And any function and its inverse compound this way will result in x. Okay, so now the calculus part. Let's look at this theorem first. if function is one-to-one and it's continuous function, because of course we don't like at the moment any discontinuity. We like the nice and smooth curve, continuous function. That means one-to-one continuous function defined on the interval, then its inverse is also continuous function. Because we inverse even using this geometric property that is the mirror image of the original function, then if this is continuous function, then the inverse is also continuous function, okay? And then I have another property, which actually is the bottom one. That means, yes, if the function is one-to-one and continuous function, it's reflecting about the y-axis, we have no breaks. That means what I can say, oh no, I still need, that's what I was thinking. That means this is still the same. Okay, everything the same. No, I need my slide, this one. That's what I was thinking. Okay. That means now, if I will have a function one-to-one and differentiable function, which means continuity, of course, and no sharp corners, no cusps, no kinks, like nice and smooth curve. That means if the original function is like that, then the inverse is also like that, because it's just the reflection. Okay? That means the inverse will be also differentiable. And as soon as I know that the inverse is differentiable, I can find the derivative. Okay? That means that's the point. And yeah, this is just the summary of this slide. If one-to-one differentiable function is defined on the interval, then its inverse, it's also differentiable, okay? Except where its tangent is vertical. Okay, we do have one exception, and actually, I can come back, maybe. Oh no, okay, I will not. I will try to squeeze. This is the function which we actually talking a lot, x cubed. Because you probably remember from calculus 1 that function x cubed at 0 has a horizontal tangent. Horizontal tangent, right? Because we know 0. It's still not like local extreme values, but it's horizontal tangent. Now, when I flip this and when I draw an inverse, x cube root of x. I should be a little bit more precise. And what we will have at 0. Yeah, if that was horizontal tangent, this tangent is gonna be, of course, vertical tangent. Vertical tangent. Because a part of that point, function is nice and smooth, it's definitely differentiable. But the horizontal will switch for the vertical tangent. And can you tell me what's the slope of the vertical line? What is the slope of the vertical line? Of course, it's undefined. In theory, we can say it's undefined. And since the slope is undefined, no slope, no derivative. That means this is the exception that, yes, that at this point, we will not have derivative. Function will be not differentiable. That means this is like just one point. But still, any other points has the derivatives. Yeah, we have to just exclude this one. Okay, that means now the second formula, because what we have to do, we have to find out how we can differentiate the inverse function, okay, inverse function, not really having a formula for the inverse function. Okay, probably sounds weird, because normally what I can do, if I will ask you for the derivative of the inverse, I will give you x cubed, okay, and then I will say, what is the derivative of the inverse for this function? That means you will probably take this, you will get an inverse, the nice explicit formula, which is cube root of x, and then you will try to differentiate, of course. And then if I want the derivative, let's say at the point 2, you will substitute 2, okay? But what I'm thinking, like what I mean saying no formula, Oh, Michael is asking a question if in this class the limits are unbounded or infinite. You can say either way if you understand what this means. That doesn't really matter. We can say unbounded, but I think infinite, because we will call infinite limits. That's what the textbook is using, but I will understand unbounded. Okay, okay, let me come back. We would like to get, because what is my point? My point is that not always will be easy to get the explicit formula for the inverse. But we still want to know how the derivative behaves, especially at one certain point. Okay? That means we would like to find the derivative, which I can actually write, f inverse prime, at the certain point. I have to find out what is the derivative of the inverse at the given point without having a formula of the inverse. All right, that means let's see how we can play with this. I will start with one of the cancellation equation. F of f inverse of x is equal to x. Everybody agrees with this. And then I will try to differentiate. In order to differentiate this, I will use the implicit differentiation. I will differentiate the left and the right-hand side, of course, with respect to x. Right? That means I will try to differentiate with respect to x the left-hand side and differentiate with respect to x the right-hand side. Can you tell me what's the derivative of x? Of course, thank you. You're not sleeping. Okay, that means on the right-hand side, you will see 1. But now on the left-hand side, we do have a compound function. That means we have outer function and inner function. And derivative of this is derivative of the outer function times derivative of the inner function. Follow the chain rule. Let's see. That's the times. That we do have derivative of the outer function, still the same input, times derivative of the inner function, which is actually the derivative of the inverse, equals to 1. And what we're looking for? We're actually looking for this derivative of the inverse. This means that I will divide both sides by that expression. I did divide, that means I have 1 over this. Okay, that means this is, I have on the other side, this is the formula that I'm looking for. F inverse prime of x equals to 1 over f prime of inverse. I know, sounds f prime inverse, f inverse prime, f prime inverse. You can see it's just, they just replaced. But what I said, I need a specific point. That means let's look at the formal definition. Of course, function is one-to-one differentiable function with the inverse exists, f inverse, and just denominator is not 0. I have to type this. Then the inverse function, it's differentiable at a, at the point a, and has this formula. F inverse prime at a equals to 1 over f prime inverse at a. It's just the switch. Okay, that means this is the second formula for this section. The first one was just the definition of the inverse. This one is the formula for the derivative of the inverse at the point A. Okay, and let's see how we can use it. The first question. If the function f of x is defined as a 1 over x minus 1 and x is greater than 1, that's when we can see we did restrict the domain, okay, then calculate the inverse derivative of inverse at 2. Okay. That means this function is not bad. You can probably go around, or I don't want to say cheat, but you can probably still use the algebra way to get the inverse, because it's not difficult. If I will rewrite function like that, then I will interchange. Y will become x, and x will become y. That means I do have this, and I can try to solve this equation for y, no problem, and then differentiate y, and then substitute 2. Okay, probably no problem, but that's not the way I want. And we can see I'm not using my funny formula that I just introduced. That means that's not the way. Let's actually use the formulas, because not always, as I said, will be easy to get the formula for the inverse. Okay, that means first of all, since we're talking about the inverse, I would like to prove that this function is 1-to-1. Okay, I would like to prove that it's 1-to-1. That means what we remember what I said. We can try. Oh yeah, that's just the. We can try to look at the derivative of this function, and hopefully we will see that the derivative is always. Actually, that's supposed to be my question for you. Because do you remember I said, okay, maybe you didn't get. I said that function is 1-to-1 if 1-to-1 if it's strictly increasing or strictly decreasing. And now it's the question, do you know how can I check if the function is increasing or decreasing? What I have to do, what I have to find. If I would like to find an intervals of increase or decrease, do you remember what tool? We have to find, yes, critical numbers, which means we have to find the derivative. Okay, slope, yes, derivative. That means let's actually rewrite this function like that. X minus 1 to the power of -1. Right? This is just this function. And now, derivative. I will use the chain rule. -1 x minus 1 to the -2, I mean power rule, times derivative of the inner function, which is 1. Let me rewrite. -1 will go on the top, and x minus 1 to the -2 will become, the exponent will become positive if I will place everything in the denominator. That we can see this is derivative, and having denominator squared will give me always positive number, and on the top I have negative. That means this derivative, it's always less than 0, always negative, which means function is strictly decreasing. Okay? It is 1-to-1 because derivative is always negative. Okay? That means if it's strictly decreasing, it is 1-to-1. Okay, but this was just the proof of 1-to-1. Now, let's focus on the main question. We have to calculate f inverse prime at 2, and that's the formula. 1 over f prime inverse at 2. Okay. That means I see this. I have to find what is f inverse at 2. And let me name this x. Okay, that means if this is x, I just name x. I don't know what it is. Right? That's because I would like to find out this. I will have 1 and then derivative at x. Hopefully I can find x. That means f inverse at 2 is x. In order to solve this equation, I will interchange. Okay? I will use the definition, and I will say f of x is 2. Do you agree with that step? Yeah, can you see? Yeah, it's just what we did. We can, f of x is 2, f inverse of 2 is x, interchanging x and y's. Okay, I do have the formula for f of x, which is 1 over x minus 1 is equal to 2. And now I simply have to solve this for x. I can cross multiply, and then I can add 2 to the both sides. I think it's 3/2. Yeah, are you okay with this? I kind of jumped, but if I will cross multiply, I will have 2x minus 2 is 1, and then 2x is 3, and dividing by 2, I have 3/2. Okay, excellent. That means x is 3/2. Oh, actually, I did type this. Sometimes I'm typing, sometimes not. And then I can substitute that 3/2. And now we can see the only thing that I need, actually, I need the derivative, which I do have derivative because I was proving that the function is 1-to-1. That means I can take this derivative because y prime is the same like f prime and substitute 3/2. Oh, I do have the final answer, but let me substitute f prime at 3/2 will be -1 x minus 1 squared, but my x is 3/2. You can try to help me. 3/2 minus 1 is half. Half squared is 4. And the reciprocal is -4. But please remember that -4 actually goes to the denominator. Okay, that means that's not a final answer. The final answer is this one, -1/4. Okay, which actually, okay. That means you can see what we did. We did get the value of the derivative of the inverse at the point 2 without having an inverse. Okay, that means that's the thing. Let's solve one more question like that. Oh, actually, that's the multiple choice. Okay, that's what you can expect. Not always I will have multiple choice during the session, but occasionally. Okay, find derivative of the inverse at 7 for this function. Square root of x cubed plus x squared plus x plus 46. Okay. That means for this one, since all of the options exist, I will assume that this function is 1-to-1. Okay? That means let's assume that the function is 1-to-1. However, we will still need the derivative. Okay? Because we remember we need the derivative. Actually, let's maybe start with the derivative of the function. Because what I'm assuming that overall domain of this function will tell me that the quantity inside, which is x cubed plus x squared plus x plus 46, must be positive. I'm not going to solve this third degree polynomial inequality at the moment, but this must be positive since it's sitting inside the square root, the even root. Okay, but we know that we will need the derivative. Did I type the solution? No, I didn't type because I don't want to write on the, okay. Let's find the derivative. We have square root of the inner function. That means derivative of the square root is 1/2 identical square roots. Yes, we remember that. Okay. And times derivative of the inner function. I can put on the top. 3x squared plus 2x plus 1. Okay, and looking at the derivative, I definitely see that the denominator is positive because based on the domain. And I'm assuming that this quadratic function must be also positive. It's the quadratic function, parabola, open up because the leading coefficient is positive. And I believe we don't have a critical points. Am I correct? I think that means it's just the parabola sitting somewhere like that. That means it's always positive. I'm just trying to look at this is positive, this is positive. The whole derivative is positive for all of the numbers in the domain, which means function is strictly increasing. Okay, strictly increasing. Okay, but this is just, we will need this, but let's solve the problem. Okay, that means we have to find out derivative of the inverse at 7. It's equal to, and that's our formula, 1/f prime f inverse at 7. Okay, and we remember we have to find out this f inverse at 7. This is my x. 1/f prime at x. And we'll use colors for you. Okay, let's work on this one. F inverse at 7 is x, then f of x is 7. Let's copy a function. Function looks like square root of x cubed plus x squared plus x plus 46 equals to 7. Wow. Now, we can try to put a little bit of algebraic steps, but I can tell you this is actually the thing, that it's not easy to solve this equation for x. Yeah, because it's that square root. I can square both sides, and I can have 49 on this side. That means I can eliminate this. I don't know, I can possibly subtract 46, which normally is not x cubed, x squared plus x. Subtracting 46, I have 3. But the 3 should be on the right, left-hand side. But this is the moment that we can't really solve this equation fully algebraically. What we have to do? We have to take an educated guess. That's what do you think? What x value? Yes, that's what x value will give me 3 on the right-hand side? Of course, 1. That means I can tell you, you can expect questions like that, and you can expect an equation that you kind of have to guess the answer. Okay? And since the function is 1 to 1, only one value of x will give me 3. Okay? That means, of course, 1, it's the good solution. And I can tell you, don't worry, because you don't have to pick, like, you don't have to try an error. You don't have to try lots of numbers. Always check 0, 1, -1, 2, -2. Okay? Just numbers like that. Okay? That means definitely 1. 1 cubed plus 1 squared plus 1 will give me 3. That means x is 1. Okay? But we did guess. And if you will practice, you will also guess without the problem. Okay? That means this is 1. F prime of 1. Okay? That means now I have to just find the value of the derivative at 1. Who can substitute 1 to this formula? That's my derivative. And I am looking, 3/7. But 3/7 is not, okay, Ryan. You said the derivative. Then we have to flip it because we have to put in the denominator. No, it's okay. Luckily, this number is not on one of the options. Okay, I can put 1 to the derivative. 3 plus 2 plus 1, 2, and 1 plus 1 plus 1, 46. This is 6, 2, and of course this is 49. 3 over square root of 49 is 7. Okay? That means we putting this quantity in the denominator. 7/3 is the final answer. 7/3. Yeah, we will try. When I create a multiple choice, I never put this value because I would like to test everything, but not silly mistake like this one. Okay? That we can see, we have to know. I can maybe use blue again. That's the formula, which was the first one, and this is the formula for the second one. The first one and the second one. Okay, that means 2 formulas from section 6.1. Not 1.6. Okay, that means that's everything. I know that I said that my session shouldn't be longer than 60 minutes. Hopefully I can squeeze, we have 10 minutes left. I can squeeze a little bit from logarithmic and exponential function. And do you remember, as soon as I don't have time, you will always have additional video on Canvas provided for you. Okay, that means that's everything. I do have one more question, but this one is more like homework question. Okay, that means this one is a little, it's still nice question. You can try to solve it. I can provide the solution, but it's more like homework exercise. This one, it's a typical quiz and exam type question. Okay, let's see this section. That means what I just said, I said that we have logarithmic and exponential in this section, and we have three main components. We have to know the limits, we have to know derivatives and integrals. That means let me try to cover limits, and you will have the video about the derivatives, and the last week is the integrals. That means don't worry for the integrals. Okay, limits means that we have to know how the logarithmic and exponential function looks like, how they behave, and then we can look at the behavior at the certain point. That means what we have. We do have this. That's, of course, the algebra, pre-calculus. I copy for you a few laws of exponents. Probably you remember when we multiplying the same bases, we can add the exponents. When we dividing the same base, we can subtract the exponents. If we have like a to the power of x and to the power of another number, then we multiplying the exponents. And a and b taken to the power of x, of course, we can like take the a to the power of x and then b. I mean, that's a little bit of exponents. And now the formula for the exponential function is simply a to the x. A is the base and x is the exponent. And this is called exponential function because x is placed in the exponent. As simple as it is. Domain for any exponential function is all of the real numbers, because I can take a to the power of any number. However, taking a value a to the power of any number will give me some restriction to the a, because x, for example, could be 1/2. 1/2 means the square root of a. Right? That means you can see right away that if I have even root, I can't have negative numbers. That means what is really important, extremely important, a base for the exponential function, it's always positive, always. And actually, we're not even including 0, because 0 to the power of any number will give me 0, and it's not really like nice function. It's not an exponential function. Also, okay, you may see this one, I have the graph, but also the base a, it's positive, but also it's never equals to 1. Of course, not 0 and not 1, because if this will be 1 to the power of any number, it's just 1. That means function like that. It's just horizontal function, constant function, linear function. It's not an exponential. That means we actually skipping. This is not the part of the exponential function. Okay? Okay, that means what we have, base is always positive, could be less than 1 or greater than 1, but never 1. If it's greater than 1, like for example this one, let me put 2 to the x, then the function looks like that. We will not plot the points, you probably remember. And we know how powerful is the exponential function. It's growing extremely fast. Yeah? We can move just a little bit of values on the x, and the y values, the height, grows extremely fast. Okay, and if the base is less than 1, of course positive, we may have, for example, 1/2 to the x. The function is just the mirror image with respect to y. It's decreasing. Yeah, that means it's decreasing quite fast. This one is increasing, this one is decreasing. That means if the base is less than 1, it's decreasing. Greater than 1, increasing. Okay, some properties. Now, that's what we have. We do have two values. Oh, if a, I can stick to that 2. 2 to the x and 1/2 to the x. Base greater than 1, base less than 1. And what we have to know? We have to know the limits. And in this case, I will just indicate the end behavior, how the function behaves at positive infinity and at negative infinity. That means if x is approaching positive infinity, if x is getting really, really big, the values are also getting big. Okay? That's when we understand this. It's infinity. If the x is getting in the negative direction, we can see the pink curve is approaching 0. Yeah? Because exponential function like this one, the simple one, it's never negative, because if the base is positive number to the power of any number is always positive. And we can see the graphs are placed above the x-axis. Okay, that means that's two limits. Now this one will be opposite. As x goes to the positive infinity, x is approaching really, really big numbers, then the pink curve is approaching 0. If x goes to the negative, x becomes really, really big in this direction, the values are huge. The values are positive infinity. Okay? That means that's the limits that I'm talking. We have to know how the end behavior, how exponential function behaves at the end of the domain, positive and negative infinity. Okay, let's see. We do have natural exponential function with the base being the value e. Yes, we remember e to the x. E, do you remember the value of e? E is approximately, do you remember 2.0? 2 point, that's good. 7, I always forget the age, but I know 71. Thank you, Ryan. 2.71, yes, like between 2 and 3, closer to 3. Yeah. That means it's definitely greater than 1. The graphs looks like that. We always intersect at 1 because any number to the power of 0 is 1. Okay, that means this will be, because we also have to know the end behavior for this one. That means limit at infinity, of course, is infinity for e to the x, and limit at negative infinity, of course, is 0. Because we can see the pink curve is approaching 0 in the negative direction. Okay, we okay with this? And then what I have a few exam type, quiz type questions. Because I will not just ask you directly for the basic function, I will ask for this property, but through the compound function. Okay, let's see a few limits. Limit as x approaches positive infinity, e to the power of 1 over x. And what we have to do, first of all, we can see we do have inner function. Let's name this function t. Limit of the function e to the t. But then I have to find out what t does. T is approaching, t equals to, it's 1 over x, but 1 over x as x is positive infinity. That means, first of all, we have to compute the limit of the inner function of this inside expression. Right? That means this depends on x. That means how 1 over x behaves at positive infinity. Can you tell me this? 1 over x at positive infinity? Of course, it's 0. We remember 1 over big is small, which means 1 over infinity will always give me 0. It's really informal. Okay, that means 0. I can put 0 here. Oh, and this one is not even end behavior. I can substitute 0. What is e to the power of 0? Any number, thank you, to the power of 0 is, I can put this, oh, no, 0. Okay, that means that's not even there. But we can see we do have an inner function first. Okay, what about this one? Limit at x goes to negative infinity, e to the negative x squared. Okay, Philip? Yes, I will finish. Yeah, I know. I will finish in 2 minutes. Okay, you can, yes, please. Yeah, you can leave the classroom. Thank you for letting us know. Okay, that means now what we have, I can do the same thing. I can name this quantity t, limit of e to the power of t, and now let's check how the t behaves. T is simply a limit of negative x squared at negative infinity. And how function negative x squared behaves at negative infinity? it's still negative infinity? Or if we have function negative and at negative infinity, this is negative infinity, function goes down, right? Or I didn't even want to do this because we can't really play with infinity in the equations. But if I will place negative infinity, if I will square it, this will become positive infinity and still the negative is outside. But we can see better, that's my answer, okay? That means t is negative infinity, okay, that's better. And now, how e to the t behaves at negative infinity. We have to know e to the t. That means how e to the t behaves at negative infinity, of course, 0. Thank you. That means that's the new concept or the shape. Okay. And let me skip this one, or maybe not. That means what we can do, we can solve one more problem because I have more, and then I will stop the session and I will keep recording later and provide the link for you about the same thing about the limits, but of the logarithmic function. Okay, that we have to know the shape of the logarithmic function and how function behaves at the end of the domain, and of course at any point. Okay, that means I will do this for you later. But let's just do maybe one more. Oh, this one is nice. Exam type question. Limit as x goes to 2 from the left hand side, e to the power of 3 over 2 minus x. That means this is the entire exponent. You can try maybe without me, e to the power of t. But t does something, and I don't know what. T is defined as a limit as x goes to 2 from the left, and this is my exponent. Okay, 3 over 2 minus x. X is 2, but not really 2. 2 from the left. That means if I will put 2, this is from the left, I will have 3 over 0. A number over small number, of course, is big number. Yes, that's another informal. 1 over small is big, which means 1 over 0 is infinity. This could be from the left or from the right, which will affect positive or negative infinity. That's actually what we have to test. Again, this is extremely informal calculation. Okay, that means 2, we have to check if this is from the left, if it's like a negative values or positive values. 2 from the left, can you give me the value for 2 from the left hand side? 1.9. Yes, why I'm thinking, because I'm thinking about negative 2, I don't know why. Okay, 1.9 or even closer, 1.999. That means 2 minus 1.9 will give me positive, right? Positive values, small, tiny, 0, but positive. Okay, thank you, Joe. And 3 over small number positive will give me huge value positive. Okay, that means how function e to the t behaves at positive infinity. Who can give me this? This will be the final thing. Of course, this is e to the t. As x goes to positive infinity, function goes to positive infinity. Okay. Okay, that means I'm sure you're confident with the exponential function. And as I said, please watch the video for the logarithmic. And I will also add a video for derivatives, because now we have to just know how to differentiate exponential and logarithmic. And this will be everything for this week. Okay, inverse, and then limits and derivatives of the exponential logarithm. Okay, thank you for joining me. And this is end of the session number 1.